Good evening. Hello, everyone. This is the Saturday Masterclass, and it's the 17th of May. Last week, we tried to figure out why we can't learn. And this week, the interesting thing is we will give you a solution to that. So, it's chapter 2 of the book Productive Failure, the solution, productive failure. Let us start with a little thought experiment. Imagine you are a child and you love playing with toys. Suppose you were part of an experiment and I randomly assigned you to play in one of two groups, group 1 or group 2. So today we are doing an experiment together. Let's see how we take this. To both the groups, I say, hey kids, here is a new toy. You have not seen this toy before. Do you want to play with it? Both groups enthusiastically show they want to play with the new toy. To group 1, I say, wait, this is a new toy, so let me first show you how to play with it. Watch and learn, and then I will let you play with the toy as you like. Once I'm done showing, I give them the toy and observe how they play. To group 2, I say, okay, here's the toy, play as you like. I give them the toy and I observe how they play. So the groups are such, in one case there are instructions, in the other case there are no instructions. Both groups are allowed to play freely with the toy as they like, except only group 1 is first shown how to play the toy. The question is, which group do you think would be more inventive in playing with the new toy? If you think it will be group 1, type group 1 in the chat box. If you think it will be group 2, please type group 2 in the chat box. Do that, and then we will see how we take this ahead. I'm looking forward to your answers in the chat box. Okay, Shalu Sharma says group 2. Let me see how many people type. Good evening. Thank you all so much. You need to type which group do you think will be more inventive, innovative. Okay, some of you are saying group 2, so I consider group 2 is the favored choice. I have done this thought experiment with thousands of people who have attended my talks and workshops over the years. Invariably, most people intuit in favor of group 2. And then I ask another question. Which group will better learn how the toy works? This time, most people intuit in favor of group 1. What if this was not just a thought experiment and there was actual scientific evidence to test the two intuitions? These are both intuitions which you have marked. Luckily, there are precisely such studies, for example, by development psychologists Z. Lin Sim and Fei Zhu in 2017 that help us understand the two questions empirically. In a nutshell, studies have shown that when children are allowed to play freely with the toy, like Group 2, they are more than 3 times as inventive as when they are first shown how the toy works and are allowed to play, like Group 1. This supports our first intuition. However, when it comes to learning how the toy works, both groups learn equally well. This does not support our second intuition. It turns out that group 2 children play in a way that helps them generate evidence not only about how the toy works, but also how it does not work. That is failure evidence, which was crucial for them learning on their own how the toy works. And if one knows both how some things work and does not work, then it is reasonable to assume that the learning is deeper. In other words, Group 2 children not only learned how the toy worked, but also how it did not. And together it helped them learn more deeply without any explicit instruction whatsoever. What is additionally intriguing about these findings is the lower inventiveness of Group 1 children compared with Group 2 children. Group 1 children went into free play without knowing how the toy worked. Group 1 children went into free play knowing how the toy worked. Even armed with more knowledge, in fact, correct knowledge, Group 1 children still did not exhibit more inventiveness during free play. Should knowledge aid invention? Or could it be that more knowledge somehow constrained them in their inventiveness? Something to ponder, for we shall return to it later on. If a child's free play with toys is so powerful, perhaps we can start to think of new knowledge, concepts, ideas also as toys. Not as physical toys, but conceptual toys. We could then argue that deep learning and inventiveness come from playing with new toys, new concepts, new ideas, exploring them, tinkering with them, connecting with them, and of course, failing as well. What implications might this have for how formal learning in the schools is organized? For the most part, and evidence backs it up, formal schooling or training in general generally follows Group 1. Mine was definitely so, and chances are you were mostly in Group 1 too. If you were in Group 1 when you were learning, please type yes in the chat box. That's all. Where you were given instructions and you got going. How many of you will type yes in the chat box? Let us see. Brinda says yes. Gurdeep says yes. Well, the yeses are all pouring in. Good for you. If bulk of our learning experiences are in Group 1, that is, when we are shown how to play with new conceptual toys first, before any opportunity to play and explore, are we not being robbed of the opportunity to develop the very basis for deep learning and inventiveness? The answer depends on the extent to which formal concepts and ideas in the various domains maths, science, language, humanities, and so on can be treated as toys. It is one thing to figure out how a toy works, akin to figuring out how to put together an IKEA item with minimal or no instruction. IKEA makes modular furniture which can be assembled. It is quite another to learn formal and often abstract concepts such as algebra, gravity, grammar, rules, and so on. It is highly improbable that a student in high school would be able to self generate principles of algebra or calculus on their own without any explicit help or instruction. Therefore, one could expect a similar pattern of effects in formal learning environments in schooling and beyond. If, however, there is something decidedly different about formal concepts, then we obviously cannot expect the pattern to hold. Once again, we can ask science to either confirm or refute our intuitions. It turns out there is a whole body of scientific research that compares Group 1 versus Group 2 in formal learning contexts. In this body of research, Group 1 is typically called direct instructions, whereas Group 2 is called discovery learning or problem solving. We do this so often in school where we say problem solving. Today we have ways of doing these things differently in different affiliated boards. A lot of the traditional method of teaching through the state boards and the Indian national boards is through direct instructions. And the new boards which are coming up, like the international boards, there is some discovery learning. And let me mention one thing here. I think all the boards are up for a challenge in the next year or so. They all will have to reinvent. It won't be smooth sailing for either one of them. The reason behind that is essentially the way we learn is changing. And if you look around day in and day out, and yesterday we had a session at Friday Brewing Knowledge, wherein we read about new learning approaches, and we realized that what is important perhaps is that every approach should be such that it should be typically customized for every individual. Now that's where the challenge lies. Let's see how that will happen ahead. So that was an aside comment from my side. So we are clear there are two groups, one with direct instruction and the second is discovery learning. Direct instruction versus discovery learning. Imagine you are learning to cook. Direct instruction would be like following a step by step recipe with exact measures and detailed instructions. Discovery learning, on the other hand, would be more like experimenting in the kitchen with different ingredients and techniques, tasting as you go and figuring out what works best without any guidance from a recipe. Go back to your grandmas, they did discovery learning, and come back to today's era, you want a cookbook. Or imagine a math class on how to solve quadratic equations. The teacher presents the problem and explains the solution step by step on the blackboard. We all do that. Students then practice solving similar equations on their own. The process is straightforward. The teacher imparts knowledge and the student absorbs and apply it. This is direct instruction or group 1. However, if the teacher presents a problem and asks students to figure out how to apply their existing knowledge and discover the solution themselves without any guidance or instructions, that would be discovery learning or group 2. The underlying logic of direct instruction is that if you do not know the concept, the best way to learn is to tell you exactly what to do, how to do it, much like children in group 1 who were first shown how the toy worked and then asked to play with it. Whereas direct instruction is heavily structured and explicit. Discovery learning emphasizes active engagement and self exploration as the primary drivers of acquiring new knowledge. The underlying logic of discovery learning is that learners should be given opportunities to learn through problem solving with minimal or no guidance so that they can explore and discover new knowledge themselves. Such like the children in group 2 allowed free play to discover how the toy works. Direct instruction and discovery learning therefore represent two ends of a spectrum in the teaching methodologies. I'm quite sure this is very simple for you to take in. And you do try these things to suit the needs of every learner. Some learners learn with direct instructions, the others learn with discovery. You face this in your classroom every day. We can now return to the question, which is better in formal learning context, direct instructions or discovery learning? When pitted against each other, science is clear and robust on this question. Direct instruction beats discovery learning hands down, sorry. In experiment after experiment, regardless of age, gender, domain, and so on, students who learn through direct instruction outperform those in discovery learning on a range of learning outcomes. It seems the pattern of effects we saw in free play with toys does not extend to formal learning contexts. Playing with physical toys to figure out how they work is different from learning domain based formal concepts. The learning method that optimizes the former seems to fail spectacularly for the latter. By the time I started my doctoral studies in the fall of 2003, this was largely the state of this debate. All done and dusted. Direct instruction had won. Direct instruction was king. Discovery learning had lost. Searching for a problem. The hardest part of doctoral studies is finding a problem. Here we are, We are asking you to do assignments. We are asking you to submit some form of study, and we are all making an effort to do it. Last week, when we met, we have seen one example where you have reached a long way, but yet the hardest part of a thesis or a presentation or an analysis is finding a problem. So once you find a problem or a problem statement, that's the starting point of your learning odyssey. This intellectual odyssey, while daunting, is a rite of passage in a doctoral student's academic growth. To quote Albert Einstein, the formulation of a problem is often more essential than its solution. In my experience, it is not unusual for a doctoral student to take years to find and formulate a problem well. Solving the well formulated problem is usually relatively fast by comparison, but it has to be a problem that is worthy of solving. One of the frequent arguments that junior doctoral students make when proposing a problem is that no one has yet solved that problem. I confess, I too have made this argument as a doctoral student, and my doctoral students have also made this argument. Although logical, this argument is weak. Maybe no one has solved the problem because it is not a significant problem to solve. Best leave it alone. Instead, find a problem which is solved, will advance the field in a significant way, and in doing so, contribute to your understanding of human learning. How does one find a problem like that? As a doctoral student, I remember spending weeks and months thinking about this. This quest, like an intellectual treasure hunt, demands patience and grit. So, your master class is going to test your patience and grit if you are going to attempt what we call assignments. It can be quite a frustrating journey. One has to wrestle with vast amounts of literature, each study a potential clue. Ideas emerge, flicker, then fade under scrutiny. Rigor battles creativity, while the specter of insignificance looms large. It's a cerebral marathon that not only shapes the thesis but also one's academic identity. And one never knows how long it would take or when we might stumble upon an insight. And then one day I was discussing Thomas Kuhn's book, The Structure of Scientific Revolution, 1962, with my close friend and fellow doctoral student John Voclis. We were discussing Kuhn's description of the paradigm shift from To- Ptolemy's geocentric model of the solar system to Copernicus, sorry for that slip of tongue, heliocentric model. It was fascinating in and of itself how the entire shift happened. Insightful for anyone wanting to understand how scientific revolutions come about. But it was also particularly insightful for me as a doctoral student. Now let us see what Dr. Manu Kapur discovered. The geocentric model, if I may ask you to discover after this session, just find out what the geocentric model is. Please Google it. The geocentric model, that the Earth is at the center of our solar system, proposed by Ptolemy, was the prevailing paradigm for centuries. It had explanations for why the planets moved as they did, including epicycles, little cycles that planets made while orbiting Earth. But over time, astronomers began noticing anomalies. The planetary movements didn't always align with the geocentric model's prediction. Copernicus proposed a radical new paradigm, a heliocentric model, that the Sun is at the center of the solar system, where Earth and other planets orbit the Sun. His model explained the observations more simply and accurately. As classic and beautiful the story of this paradigm shift is, it didn't happen quickly. What struck me was how a string of anomalies with the geocentric model to the questioning of the most fundamental assumptions that the earth is at the center, which allowed Copernicus to entirely revise centuries of established science by questioning just one fundamental assumption, yet changed our understanding of the solar system. Much like a Jenga tower, you remove one critical foundational block and the whole thing falls apart. I went back to thinking about the debate between direct instruction and discovery learning, and how direct instruction and had basically won. But there was a problem. Actually, not one, but at least three. So let's see what the three problems are. First, even though direct instruction was the prevailing model, there were still lots of anomalies or problems with direct instruction model. As noted in the previous chapter, especially Anne Schoenfeld's seminal paper on when good teaching leads to bad results, reports of direct instruction resulting in shallow understanding were coming in thick and fast. Retention problems, understanding problems, transfer problems. Evidence on the problematic aspects of direct instructions had started to gather momentum, much like the accumulation of anomalies in the geocentric model. Second, even though direct instruction had won and it was the prevailing model, it did not mean a new model couldn't be better, just like the heliocentric model was better than the geocentric model. There could be models that were even better than direct instruction. Third, just because discovery learning lost, it didn't mean all was lost. No doubt students do not succeed in solving problems without any guidance or support. But that does not necessarily mean the problem solving experience has no value. Maybe there was some value in the problem solving efforts, in the struggle, in the frustration, in the exploration that ultimately results in failure. Maybe this value needed to be extracted somehow. There had to be a way. This was my aha moment. I remember it vividly. It was neither grand nor explosive, just a quiet triumph. Everything else seemed distant in that moment, muted against what felt to me at the time a striking insight. I could zone in on the fundamental assumption and go after it. I now understand why direct instruction model assumed that the best way to teach a new concept was to explain clearly and exactly what the concept is. There was no point in learners struggling with problems when you could tell them exactly how to solve them. And today you have ways where it's so easy to do all this. Tell them what to do and how to do it. There it was, nestled in the complex workings of the model, a subtle yet fundamental assumption that could very well turn out to be a fundamental flaw. Making learning easy eases learning. This was to be the foundational block in the direct instruction Jenga tower. With this singular insight, which in hindsight seemed so obvious, my intellectual landscape shifted, a gentle earthquake that vigorously shaped what was to come next. What if I were to question this fundamental assumption? What if exactly the opposite could be true? Instead of making it so easy, could be the best way to teach, be to make initial learning hard. Counterintuitive as it sounded, I decided pursuing this line of argument would be the focus of my doctoral research. So, counterintuitive as it may sound, what he says is that why not make initial learning hard? That may be the way forward so that people learn better. Quickly, I ran out two questions. How does one make initial learning hard? And how hard is hard enough? The first question was relatively easy to figure out. One simple way was to get students to solve problems that required knowledge of concepts they did not know yet, problems that were beyond their knowledge base. Clearly, such problem solving will be hard. We try and set questions and exams, and that's a typical way of doing it. The second question, was not so easy because operationalizing hard is itself hard. How much can you challenge? That's the whole question. Where does one draw the line? Luckily, I could resort to an old trick in the science playbook. Look at the extreme case scenario. The extreme opposite of making things easy is not to make them hard, but make them so hard that it results in failure. My logic was that if I could demonstrate the hypothesis in the extreme case, then the middle ground would be easier to sort out later. I needed to engage students to problems in problem solving. That was not just hard, but one that led to failure. Speaking of extreme, if I could demonstrate the hypothesis in a domain that was known to be hard to learn, for example, mathematics, even better. What would such math problem solving look like? So now we are designing for failure. Imagine the following scenario. You are a high school student, and today's math lesson is on the concept of standard deviation, a basic math concept that measures how variation there is in a distribution. For example, if everyone in your class is of the same height, then there is no variation in height. The standard deviation of heights is zero. If, however, there are lots of different heights with the tall and short students, then the standard deviation is large. How large exactly? Well, that's the mathematical formulation that is captured by standard deviation. As a student, you do not know this concept, probably never heard of it until the lesson. You are a novice, so you come into the class, sit down at your desk, and get ready for the lesson. Your teacher comes in and starts the lesson. You expect her to teach you in the good old direct instruction way, except she adopts a different approach. Instead of teaching you the concept of standard deviation, she gives you the challenging problem in figure 2.1. We will come to that. She explains the problem to you and gives you about half an hour to attempt it. She asks you to try your best to solve the problem and emphasizes that your goal is to invent as many solutions as possible without worrying about getting them right or wrong. Take a moment to think about how you might approach this problem as a high school student who has not yet learned the concept required to solve this problem correctly. If you have time as you are reading this, take a few minutes to even have a go at it. List 3 to 5 ideas you might generate. When I ask people to estimate the kinds of solutions students might be able to generate, two things typically happen. First, they find it hard to think like a novice, especially if they are already know the concept of standard deviation. This happens a lot with math teachers. Second, they tend to underestimate what students can generate, typically limiting them to a few standard ideas such as means and graphs, ideas that you can find in textbooks. But when I actually show what students are typically able to produce, they are invariably and pleasantly surprised and mighty impressed too. Teachers like it particularly because they can see the creativity and play of imagination that students can engage. So here's a figure one. There are two Amy and Ben basketball players in a league. The table shows the number of points they have scored in 9 games they played. So on left side, number of points of Amy, and right side, number of points for Ben. Invent as many ways as possible to determine who is the most consistent player is. Just be creative without worrying about getting it right or wrong. So what I'm going to do, I'm going to take a screenshot of this and put it in your conversation in the Teachers Academy chat of WhatsApp so that you can try this exercise later. Let's see how it goes now. Likewise, there's also a big surprise for students who are they themselves surprised that they could generate as much as they actually do. There is a big gap between what they think they could do at the outset and what they actually able to do. When faced with a challenging problem, a problem that is beyond our current knowledge and skills, we tend to underestimate our capabilities and those of others too. Data, however, shows that we have far greater resources for creative production if only we are given well curated opportunities to do so. So let's look at this data to see what novices are capable of producing when they try the basketball problem in figure 2.1, which I am going to share with you right now. Let me see if I can send it across to you. Yeah, so I'm going to Saturday Masterclass and I'm sharing the figure 2.1. I'm sure it's reached. If it's reached you, say yes. You'll find it in your WhatsApp chat. I know it's a digression from the main session. You'll get it in a few seconds because I've just added it to the conversation. The ideas of a novice. So we will go that far. Remember, they have not been taught the concept of standard deviation required to solve this problem, where we are comparing two basketball players and trying to find out who is better in performance. The ideas of a novice. When faced with the basketball problem in figure 2.1, which must have reached you, students typically start by trying to figure out what consistency really means. Are we looking for the better player or the more consistent player? Is there a difference even? One of the common things students and even adults actually do is to confuse the two. Being better is not the same as being more consistent. A straight F students is more consistent than a student who get A's and B's, at least statistically speaking. Just eyeballing the data also suggests that Amy gets better over the games, but not Ben. Does this mean Amy is more consistent? These kinds of questions and discussions spontaneously emerge as students go about solving the problem. Other students may jump directly into computing something. After all, given a bunch of numbers, that seems the path of least resistance. The lowest hanging fruit is to calculate totals, that is, the number of points scored by each player, and compare the two. Averages are also intuitive, so they calculate the means. And if they have learned the concept of median and mode, they might find those out too. It turns out that the problem is designed in a way that the totals are the same. Both Amy and Ben have scored a total of 126 points over the 9 games, which also means that their averages are also the same, that is 14. He has calculated this. I will screenshot this and also place it for you. To give you some things to think. This is deliberately designed into the problem. I will discuss the design principles in greater detail in chapter 3, but the idea is that the problem invites students to use their intuitive as well as formal knowledge learned in school. Yet, the problem is designed in a way that those solutions do not work because totals and averages are the same. They cannot distinguish between Amy and Ben. This way, it becomes clear to the students that they have to think of something else. Another common solution is to draw graphs, most frequently by plotting the number of goals in the y axis against the game in the x axis, as shown in figure 2.2. Here's the figure coming to you. Okay, so I add this figure also here. So you're getting some food for thought. This way, they can see how the graphs changes from game to game. If it goes up and down a lot, has a lot of changes or fluctuations, then the player is inconsistent. If, however, the graph does not change much or has only small fluctuations, then the player is more consistent. One can clearly see from the graph that Amy's graph either stays the same or goes up, but never down. Ben's graph never stays the same and goes either up or down. Hence, Amy is perhaps more consistent, they would argue. Other visual presentations that frequently emerge are tally tables, frequency polygons, or histograms. These visual representations are indeed a great way to get a feel of the problem, but they do not constitute the solution in and of themselves. In that sense, they are necessary but suboptimal. We praise students for generating visual representations to understand the problem and look for patterns. But then we push them to use these representations to generate solutions that are quantifiable and more precise, just like mathematicians would. The cycle of invention needs to carry on. Having looked at the totals and averages, students start to look at the ends. What were the maximum and minimum numbers of points scored by each player? In other words, what is the range of scores for Amy and Ben? You might have guessed. The problem is designed in a way that the minimum 11, maximum 17, and the range maximum minus minimum is 6. Same for the two players. Once again, the problem invites prior knowledge, but it is not solvable by that knowledge. They need to think of something else. Here is where things start to get really interesting. One intuitive solution that turns up frequently is to calculate difference between the points scored from one game to the next. That is, the second game minus the first, and the third minus the second, and so on, until the ninth minus the eighth game. A total of 8 game-to-game changes. Adding all these differences gives the sum total of all the changes from one game to the next. If you calculate this, then Amy's total game to game change turns out to be, so you're minusing it and he's calculating it, 6. Similarly, Ben's total game change turns out to be 4. Let me also give you this, because as we don't have a book, these visuals may help you think a little and help you design a productive failure exercise at your end. So one more visual gone into Saturday masterclass. Since Ben's total is smaller than Amy's, perhaps Ben is more consistent. Or so they would argue. Some students notice that Amy never has any negative changes, but Ben has both positive and negative changes, which cancel out each other. This is, of course, fair, they would argue, and hence propose that only the magnitude of the change ought to be considered and not the sign up. Upon recalculation, Amy's total game to game magnitude of change is still 6 because she has no negative changes. But Ben's is now 24. What a jump from 4 to 24. Clearly, Ben is now more consistent by this measure. Finally, some students go on to calculate the average magnitude of the change. For 9 games, there are 8 changes. Therefore, the average magnitude of change from Amy equals 6 out of 8 or 3 out of 4. Whereas for Ben, it equals 24 out of 8 or 3. By this measure, Amy is again a more consistent player. There are now several such studies with thousands of students around the world, not just on the topic of standard deviation, but many topics from elementary to middle to high school and universities. In math, but in other domains too. I use the basketball problem here as an illustrative example. Altogether, the idea is to design problems so that students are able to generate about 4 to 6 solutions. In the case of basketball problem, it is often a mix of totals, averages, range, graphs, and weighted calculations of game-to-game changes. This typically takes 30 to 45 minutes of problem solving. While all the solutions are highly intuitive, they are either incorrect, example totals and averages, or best optimal, like graphs, range, game to game change. None of these solutions are correct from a canonical point standpoint, which is calculated using the formula of standard deviation. The target concept for the lesson. Therefore, one may ask, what is the point of engaging in such an exercise when it results in either incorrect or suboptimal solutions? This is precisely the reaction of the proponents of direct instruction. When they look at this, their immediate reaction is, see, we told you students will not be able to generate the correct solution on their own. You have just wasted time. What could possibly be gained from engaging in such an exercise? If students don't know the concept first, what is the value of getting them to solve problems that require knowledge or that very concept? You should first have taught them first. Yet, when I share the data with people, most of them, particularly teachers, educators, parents, and even students themselves, find it intuitively obvious that there is something that even if students are not able to generate the correct solution. It is like group two children playing with the toy without knowing how to play with it. But to others, especially the proponents of direct instruction, such an exercise carries no value whatsoever. It was clear, even though it is intuitively obvious to many, including myself, that such an exercise has intrinsic value. Intuitions cannot be admitted as scientific evidence. It is not just sufficient to merely illustrate students' capabilities when they engage in problem solving deliberately, designed to lead to failure. I also needed to find a way to extract or bootstrap that failure for deep learning. How does one do that? We'll take a pause here. Let me just flip and see. Yeah, I think we will take this ahead next time. So I'm bookmarking here where we will turn direct instructions head on. I will add the bookmark here and we will go to the Saturday masterclass. And share this bookmark. So this will be the bookmark for next Saturday. You need to think because this is an interesting way of learning as we read together. So bookmark for 24th May 2025. You've got the bookmark, please place it there. Yeah, and one more small request. Can someone please help Kanishka Roy Chaudhary? I did help her last time, but she's perhaps the only one who has a problem and who says you can't join the meeting. So there are two things you need to solve at your end. One, you have to register from your email ID. In that email ID, you will get a response, and in that response, there'll be a button below to join. That's the way you join. And in case that doesn't work, then the other way out is you simply register with a different email ID and register the second time. That's the second way out. And third way out, again, like direct instruction failure is get back to us, we will delete you, and you can then sign in with the same email ID again. We are actually allowing you to sign from multiple devices to overcome this problem. So you have to find the solution. We can't do more than that. And finally, the solution, sit with a friend and do it. So thank you all. It's been a wonderful masterclass this Saturday. I enjoyed reading the book. I am not really sure if all of you enjoyed listening to my monotone. If you have any questions, please pop in the chat box. There is an answer from attendees. Let me see. Where is it? Yeah. Yeah, Brinda. Brinda, you signed today as a participant. Please come in. Brinda, please talk.
Yeah, I'll just talk. Um, Sandeep, I just wanted to say one thing right in the beginning when you were talking about the two groups. So, when Lego came out with its set of blocks, there was no instruction manual. And the study says that what was produced by children who were using the Lego toys was so creative and they made so many different kinds of things. But there came a time when Lego brought out an instruction manual, and children then started following only the manual and not doing their own stuff. So that's the intrinsic difference between allowing children to explore without giving them the instructions of how to go about doing something, because they will stumble, they will fall, but they will rise. So that's what discovery learning is all about. This is what I wanted to share right at the beginning when I raised my hand, because I think a lot of us would like to believe that we try this to some extent in our classes, but yes, direct instruction prevails because of various practical reasons.
Vrinda is business economics.
Absolutely, absolutely. But
But
then I
on
think,
that point, I want to add that on a Thursday session, when Subhashish joins us,
yes,
it's very, very clear he is the antithesis of direct instructions.
absolutely right.
So if people want to actually see
Yeah,
the discovery learning, you must meet Subhashish on what we call Thoughtful Thursdays. Is that right,
that's true.
Vrinda?
Absolutely correct, Sandeep. Thank you for saying that.
Thank
He'll
you,
be very
Vrinda.
happy to hear this.
Absolutely. And
Yeah.
yesterday also, when we talked of new teaching and learning approaches,
Yes.
what is very uncanny, the My Good School book is written in 2020.
Yes.
Dr. Manu Kapur's book is 2024.
Mm.
And Subhashish has taught all his life of 50 plus years. But the beautiful part is we are not able to understand discovery learning even today.
Yeah. Sad.
Yeah.
Sad.
So try your new teaching and learning approaches till next
Yeah.
Saturday. Thank you, Brinda, once again. It's been a
Thank
delight.
you. Pleasure.
And this book, if you ask me, Brinda, if I was to list a book, my best read of last year, it is this book.
Absolutely right. I second you on that. And
Yeah.
as I've mentioned earlier, I'm reading that with my staff, and we keep discovering things. And there's so many things that come up, how we can make use of this. So yeah. But Sandeep, if I may just add, uh, Subhashish and I were lucky because we belonged to a school. I mean, I was initiated into teaching where there was so much of emphasis on exploration and discovery that we started believing that this is the way to teach. Unfortunately, it didn't build into an institution of that kind. It had to close. So yeah.
So, Brinda, it's very simple. I
Yeah.
want to add a little example here.
Yeah.
When we were in school, we were sent out on our own to discover and do a private midterm.
Yeah.
Private midterm means that they would send boys on their own
Yes,
to
I know. I
explore in
know
the
that.
mountains.
Yeah.
And by the way, they don't do that anymore.
Oh, that is sad.
Yeah, so this is the change that has happened now
Yes.
for the knowledge of people who are here. I am from the Doon School, where twice a year, when you were the age of 14 plus, they
Hmm.
would just let you go in a group of 5 to 8, and on
Yes.
your own, you'd have to trek for 5 days, reach a destination, manage your entire logistics of food, eating, travel with a limited amount of money they give you.
Yeah.
And
And a route.
a very powerful way of learning. And that, if you ask me, was productive failure.
Yes. Yes. Or productive success, I would say. Because the boys, you discovered your way through, and you found how to survive on a limited amount of money, and also to take lifts or hitchhike or come back and eat in the cheapest of the dhabas
Yeah, yeah,
possible.
absolutely. So
Yeah.
that's how that's
Yeah, that's
discovery
right.
learning.
Because
That's
I
discovery
remember
learning.
my son, he went to Cutling Glacier on that trek. And when he came back, I could hardly recognize him.
Yeah, yeah,
So
that is discovery
that's what,
learning, and
yes,
we all saw that way. I just want to read one or two comments so that people have written.
yes, please do that.
Rajani has written, children learn better when they have no or minimal instructions like video games. Great.
Mm,
Sumaya has written, Sandeep sir, productive failure is present inside us. How
mm,
we prove it? Please explain. That's it. I think that's what the book will tell you, Raj.
yeah,
Sumaya, let's go ahead with it. Then Rajani says, they are better learners when they search and discover on their own. Whereas we adults struggle because we look for direct instructions. Absolutely. Good one.
Very correct.
Yeah. So on that note, I think we have exhausted our time and added a few more minutes. Thank you again, Brinda.
Thank
You're
you.
such a wonderful co-traveler in discovery learning. There is an
Thank you. It's my
hand,
pleasure. I'm
Sumaya.
learning as I travel.
Yeah, yeah. Sumaya, please speak. Your hand is up. Sorry, I just saw it. Yeah, go ahead, Sumaya. You can talk, Sumaya. You can unmute and talk.
Hel- Good evening, sir. How
Good.
to improve a productive failure if it is present inside us? Can please explain it?
Yeah, I think we what I just said that let's read the book on it will present itself. Now I आपने तो पिक्चर की एंड पहले ही मांग लिया मेरे से. सो थोड़ी सी एक्साइटमेंट रखो और अगर आपने पिक्चर का एंड पढ़ना है तो एक किताब मंगा लो पहले ही पढ़ लो. So Brinda, on that cryptic answer, I know I killed her curiosity.
Yeah, I know. But then she can hold on to it. And we'll
Yeah.
all discover the answer as we go along. Yeah.
Enjoy it to find it. Thank you so much.
Thank you. Have a
Bless
good
you all.
weekend,
Thank
everyone.
you to the panelists,
Thank you,
and do
sir.
join us at My Good School tomorrow. We have a beautiful screening of episodes 17 from
Oh,
the Guru Nanak docu series, and we are now screening in Hindi. So
lovely.
17, 18, 19, 20, 21, 22, 23, 24. 8 episodes will be all in Hindi because we feel it's fair opportunity for everyone to learn language and culture if we respect everyone's language and culture. So we've actually been doing them in English. We are trying another productive failure example. We want to see, do we get more reflections if we do it in Hindi? So that's the way to do it. Thank you so much. Bye bye, Minakshi. Bye bye, Manisha. Bless you all. Gurdeep, thank you so much for doing the artwork and the posters. You do it at great discomfort, running from school bus to school every morning, every Saturday. Thank you so much for that.
Thank you, sir. Thank you.